Another thing to consider when we're designing a synthesis is how green is it? How environmentally friendly is our chemistry? Now, what are some of the things that we would want to think about when we're designing something that is going to be a green synthesis? Well, we would like it to be green for the environment, and then there's also times when we want it to be green for ourselves or a little bit safer for us. So, let's consider how we could use less toxic reagents or solvents. And here's something that we could, just an example that we could think of here. If we're going to do an electrophilic addition, I'll just put some substitution off of this benzene ring. So we'll choose a styrene, some kind of styrene derivative. And we would like to transform this into the alcohol. And we'll go ahead and do Markovnikov addition on this because we have a few options available. Then there's a couple of ways that we could do this. We could use oxymercuration demercuration, but that is going to involve using a mercury reagent. And as you may know, mercury reagents, or just mercury in general, is not very clean. It's toxic, right? We're also going to need to use additional steps to remove the mercury. We'll have to do something with it after we're done. We'll have to properly dispose of this. It's just not very green. Now, there are times when we'd like to use it, especially when there's a possibility of a rearrangement, and it could still be a good option, especially if it avoids us having to do another reaction or produces a much better yield, but it's not the best green option that we have. Now, in this case, there are no rearrangement options available, and so it would be just much better to use just water and sulfuric acid. Those are much greener than mercury. Now, there's no rearrangement in this case, and so we should explore using that. And hopefully the yields are pretty good. Now, let's look at another example. Let's add bromine to this double bond. Now, if we do this using our standard chemistry here, we could do bromine in carbon tetrachloride. But carbon tetrachloride is not a very nice solvent. I mean, it's a great solvent, but it's not a very, it is toxic in nature. So we can have carbon tetrachloride, and this will work, but there are other options. And one of those options is to use sodium bromide with this sodium bromate and you use a 5-to-1 ratio of these two reagents, and you can run this in acetic acid. Now, acetic acid is a very green solvent. In fact, it's possible to consume it. And solvents and vinegar. I would suggest diluting it before you would do that, but you can notice just how much greener it is to have something that is really a natural product. Now, so far we're looking at things that are better for the environment and in a lot of cases better for us, right? It's better to avoid these toxic solvents. We should also consider how safe a reagent is. So we could make a methyl ester using the let's finish writing this out. We can make our methyl ester. And there's a couple ways we could do that. We could use an explosive compound right here, or CH2N2, diazomethane. And like I say, this is explosive, so that's not the most desirable compound. Now, the only side product is nitrogen, and so that sounds very good. But working with an explosive may make us think, is there another way we could do this? And I know everybody thinks that chemistry is about explosions, but it's really nice when things don't blow up in an uncontrolled way. What we could do instead is place this in methanol and use some sulfuric acid as a catalyst and affect this transformation. Now, you may not get as high of a yield, but it is significantly safer. Now, let's also consider what other reagents or what other compounds we're making on the course of our reactions. So I mentioned that here, that we are only making nitrogen. That's a very environmentally friendly byproduct. But it would be nice to avoid byproducts as much as possible. I mean, in this case, we're only making water as a byproduct, so that's pretty good too. But let's look at this. Epoxidation. Now, if we want to epoxidize or form an epoxide from this, we'll just use our MCPBA. Now, MCPBA is a rather large molecule. And it really only adds one oxygen to our product, right? To our reactant, adds one oxygen there. And what we're left with is the meta-benzoic acid, metachlorobenzoic acid. I forgot the chlorine in there. So we've got this rather large byproduct here, just to add the one oxygen. And again, that might be the best way of doing this, but we'll notice that we're throwing away quite a bit of this, or we have to do something with this byproduct. And this brings up an important concept, atom economy, right? It would be greener if our atoms end up in our product. In fact, by that definition, this reaction right up here has 100% atom economy because we're taking bromine and we're adding it over this double bond, and all of our reactants end up in the product. Down here, we have much less of our reactants ending up in the product. So the formula for looking at this is the mass of the atoms in the product divided by the mass of the atoms in all of the reagents. So essentially, this is just asking how much of the reagents that we're using ends up in the product. And of course, we'll multiply by 100%. If we do this, for this particular example, you'll notice that we have a mass of about 86 grams per mole for this. This is about 70 grams per mole. And our MCPBA has a mass of, let's see here. I only wrote down the total mass. Well, the total mass of my reagents, 70 plus, I'm forgetting what the mass of MCPBA is 242.6. That's the 70 plus this. And then if we take our 86, that is our product mass, multiply by 100%. We'll see that our atom economy is only 35.4%, which is pretty low because this weighs a lot. It weighs much more than my product. And so I don't have the best atom economy with this. And sometimes that's just unavoidable. And you'll notice that this might lead to other choices. Like if we choose a leaving group that is a triflate or a tosylate, those are excellent leaving groups, but they're rather large. They contain quite a bit of atoms and they're really big. And while that makes it an excellent leaving group, it's going to lower your atom economy because fewer of those atoms end up in your product. According to this formula as well, if our leaving group is, say, an iodine versus a bromine, the bromine would have better atom economy, even though it's just one atom, right? Just because the iodine weighs more. I think that distinction is a little less useful in those cases because it is only one atom and we just have that one leaving group there. And so just because it weighs a little bit more doesn't necessarily mean it's bad. So that's where some of this can break down a little bit. In this case, though, I think it is quite valid just because of the large byproduct that we're making here. So these are some of the things that we would consider for a green synthesis.